In this example, we analyze EFE MOSFET amplifier having the bypass, having a voltage divider configuration, and then without the bypass capacitor. So there is no bypass capacitor connected in parallel with the source resistor here. Okay, so and then this is the given specification. The threshold voltage is 2 volt, and then the K value is 150 milliampere over voltage square, and IDQ is 2.6 milliampere. Small RDS is equal to infinity. So when small RDS is equal to infinity, so no need to draw the no need to include the small RDS in the AC equivalent circuit. Okay, so the first step to do the AC analysis is to draw the mid-band equivalent circuit. So we draw the mid-band equivalent circuit starting from the input port. So this is the input port VI, and then at the VI we have this one is the coupling input capacitor. So it should be short circuit. So this is short circuit. And then we have R1 and R2. So R1 and R2, here the VDD will become the ground. So R1 and R2 will be in parallel. So this is R1, and we also have R2. Okay, and then we come to the gate. So the gate of the MOSFET. Between gate and the source, there is an open circuit, and then the voltage across the open circuit is VGS. Okay, at the source, this is the source of MOSFET. There is RS connected to the source. Okay, since this is without the bypass capacitor, so RS appear in the mid-band equivalent circuit. So between source and drain, we have the current source, voltage dependent current source, GM VGS, and then at the drain we have two junction. The first one is the RD1 is connected to the ground. From here, RD1 is connected to the ground, and the other junction is RD2 in series with RL. So this is RD2, and this is the RL. Okay, so this is the AC equivalent circuit at the mid-band. Okay, so the IDQ is given as well as K, so you can calculate the GM. So GM is transconductors 2 times K ID square root K ID. Okay, so this is the K is 150 milli. So K is 150 milli. It's quite high. So 150 milli, and IDQ is 2.6 milliampere. So this will give you 39.5 millisiemens. Okay, this is the GM. Okay. So after drawing the AC equivalent circuit at the mid-band, we can analyze the input and output impedance. So this is input impedance. So the input impedance is ZI. So what can be seen from the input port is only R1 and R2. So all the resistor network, all the component network, after this point, after the gate terminal point, will not be seen because the gate and source is open circuit. Okay. So Zi is equal to R1 parallel with R2. So R1 is 200K parallel with 100K. So this calculation will give you 66.67 kilo ohm. This is the answer for the input impedance. Okay. So next is the output impedance. The output impedance is here is denoted by as a RTHC2. So you say Z out is equal to RTHC2. Okay, RTHC2. So this is the output impedance that we want to calculate. So how we going to calculate this one? Okay, make sure that you aware that when we want to calculate the output impedance, we need to consider the input Vi is equal to 0. When you consider the Vi is equal to 0, what will happen to the circuit? Okay, this is Vi is equal to 0. So the Vi will be grounded, and then R1 and R2 can be ignored because this is bypass. Okay, this is bypass. So this positive plus of VGS will be connected to the ground. Okay. So actually what we do when we analyze the output impedance is we take out the load resistor, and then we apply voltage at the output, and we measure the current output. Okay, so the circuit can be redrawn something like this. Say I put it here. This is RD2. This is from the output port. RD2. Then we have here, this is RD1. So I changed the drawing a little bit. So this is your RS. This is okay. Okay. This is the circuit for in the detailed analysis. This is circuit that we are going to analyze to get the output impedance. Okay. So from this side, we will see RD1, RD2, and also as well as this GM, VGS, RS. Okay. So but if you do further analysis, okay, you may find that you can express the VGS. Okay. For example, we see the voltage across the RS here is equal to VGS. So VGS is minus VGS is equal to the current at the RS here. The current at RS here is equal to GM VGS. So GM VGS times RS. So you have this relationship. Okay, based on this relationship, so you can rearrange this equation and get this. So VGS times 1 plus GM RS equal to 0. So this mathematical expression indicate that VGS need to be 0 in order to in order to make this equation valid. Okay, so because 1 GM has a value, RS also has the value, so 1 plus GM RS will have the value. In order for this the right hand side become 0, VGS need to be 0. So VGS is 0. When VGS is 0, GM VGS is equal to 0 ampere. This is open circuit. So what will happen to this circuit? We will only see the RD1 and RD2 only. Okay, so the answer is RTH-C2 is equal to RD1 plus RD2. So this is 3 kilo plus 4 kilo. So the answer is 7 kilo ohm. Okay. Okay. Although the analysis is the proper analysis, you need to do like this. You need to redraw the circuit to confirm that to identify which component need to be considered when you analyze the output impedance. But if you go through this example, you will see that in these cases, most probably that at the output impedance, you need to assume VGS is equal to 0. So when VGS is equal to 0, the GM VGS will also equal to 0 ampere. So this is open circuit. So there will be no connection here. So what you see from the output is only RD1 and RD2. Okay, so we're done with the output and input impedance. So next is the voltage gain. Okay, let me redraw the circuit again. So this is R1, and then we have here R2. This is the VGS. This is RS. GM VGS. This is RD1, and we have here RD2. Lastly, we have the load RL. Okay, the output is the voltage across the RL, and the input is at the input port. So the voltage gain AV is defined as V out over V in. So you need to define what is V out. What is V out? So V out here is the voltage drop at the RL. So since we have the RD2 here, so there will be a voltage division between the RD2 and RL. So let's say I denote the current here is IL. So V out is IL RL. So what is IL? So IL is using the current division. IL is RD1 over RD1 plus RD2 plus RL times minus GM VGS. Okay, this is if you insert the value 3K plus RD2 is 4K, RL is 10K, you have 14K. Okay, and then GM is 39.5, and VGS, this is equal to sorry, I missed the minus here. This is minus 6.97 milli. VGS. This is IL. So the V out is equal to minus 6.97 milli times RL is 10K. And then you have here VGS, because IL is minus 9.67 milli VGS. Make sure that you do not miss the VGS. So this will give you minus 96.7 VGS. Okay, so this is V out. How about the V in? V in is voltage at here. This is V in. So from this point toward the ground, if you use this current path, you will have the VI equal to VGS. This voltage from here, from this point to point, and then you need to add on the voltage drop at the RS. The voltage drop at the RS is the current or at the RS time the RS. So the current at the RS is GM VGS. So this is GM VGS RS. So this is VGS 1 plus GM is 39.5 milli and RS is 1.5 K. Okay, this will give you 60.2525 VGS. Okay. Since you have the equation for V out and VI, you can solve the AV is equal to minus 69.7 VGS over 60.25 VGS. VGS can be cancelled out, and then lastly you should get the value of minus 1.15. So this is the solution.